6.4, exponential growth and decay. This is our last section of chapter 6, and then we will have, I think, 3 sections of chapter 7, and then we are done. So, 6.4, let's get into it. This is a lot of applications of anti-differentiation. So, I do have a quick review quiz here for you. This is all pre-calc review, so hopefully you can go back and remember some of the stuff that we did. I want you to rewrite the equation either in exponential or logarithmic form compared to what it is now. So obviously a, the natural log of a equals b, that's in logarithmic form. I would like you to solve that basically by rewriting it in exponential form. Basically it's the same as solving for a in this case. So you have a and b to solve, to rewrite the other way. And then number 2, I want you to solve for x and find out what x is, showing your work to do that. So there are, and there's a number 3, solve for y also. So we have 6 total points on this quiz for you to turn in when you come in tomorrow. What we are learning about separable differential equations, we've talked about that a little bit already in the last section. Law of exponential change, and then how that is applied to compounded interest and modeling growth with other bases. So, understanding the differential equation dy dt, that should be dy dt, is equal to ky, gives us new insight into exponential growth and decay. So, I have an example here of solving by separation of variables. The question says to solve for y if dy dx is equal to x squared y squared and y is 3 when x is 0. So, when we are asking you to solve a differential equation, we're asking you to figure out what the antiderivative is. So, what we always want to do with these is if you have an x and a y together, we get all of our x's on one side and all of our y's on the other. So that's why I have divided off here my y squared, and then I've sent my dx to the other side by multiplying it over. So I have y to the negative 2 dy is equal to x squared dx. Once I have that, I just find the antiderivative of both sides. So we're going to integrate both sides. And so when I integrate y to the negative 2, I add 1 to my power, divide by that power, so I have negative y to the negative first. And then I add 1 to my power here and divide by that power, so 1/3 x to the third plus my c. When I put my 3 and 0 back in for y and x, and I solve that, this will give me a negative 1/3 equals then 0 plus c, which is c. Final answer, when I manipulate it a little bit and put all those values back in, and then I solve for y, I will have y equals 3 over 1 minus x to the third when I solve it for y with my new c value. Okay, that is your process every time. Get your all of your x's and dx's on one side, your y's and dy's on the other, and then integrate everything, and then solve for c. This solution is valid for the continuous section of the function that goes through 0, 3. So if we notice down here, my domain here is all reals except x equals 1. So because 0, 3 is on the other side, it only pins down that section from negative infinity to 1. So we say that this is only true for sure that we know of for that continuous section from negative infinity to 1. Alright, so let's talk about some applications. The number of bighorn sheep in a population increases at a rate that is proportional to the number of sheep present, at least for a while. That should make sense. That is the truth with any population situation. The number that we have increases at a rate that is proportional to the number that are already there. So my next point here says, so does any population of living creatures. Other things that increase or decrease at a rate proportional to the amount present includes radioactive decay, money, also in an interest-bearing account. If the rate of change is proportional to the amount present, the change can then be modeled by dy dt is equal to ky. Let's talk about why that is the case. the rate of change, that's dy dt, is proportional. Hopefully you remembered that back in pre-calc, whenever we talked about that is proportional word, we had to set that equal to a k value. That k was a constant that we had to find later using information that we were given. So we have the rate is proportional to the amount present at the time, the y at the time. So we have dy dt is equal to ky. This is our differential equation we're going to discuss. So, our rate of change is proportional to the amount present. Let's solve this differential equation. So we get all of our y's and dy's on one side and all of our t's and dt's on the other. So I sent my y over and I just left my constant here at the front and I sent my dtu to the other side. When I integrate both sides, I now have this derivative right here of 1 over y. Well, the 1 over y is the derivative of the natural log of the absolute value of y. And then this is just a constant. It's any number. So if I find the antiderivative of k with respect to t, it's just going to be k times t plus c. So, moving on. If I just want to solve this for y, I want to get rid of my natural log, so I raise everything to the power, or to the base of e. So my e and natural log cancel out, and I'm left with the absolute value of y is equal to e to the c times e to the kt. Remember, a plus in exponents refers to two bases multiplied. Okay? And then to get rid of my absolute value, I just do a plus or minus on the other side because either the positive or the negative value will give me y. Alright? Now, the reason we have changed the plus or minus e to the c out for an a is because that is going to be my constant. If you think about it, plus or minus e to the c is the constant value a. It's just going to be a number. So since we say it's a constant, we're just going to set plus or minus e to the c equal to a, which refers to the amount that I have at the very, very beginning. And that's why we have a y sub o, or a y sub 0 out here. It's the amount that we have at the very beginning of time. So when t equals 0, my e to the k times 0 cancels to become a 1, and so my y sub 0 is a. So y is equal to y sub 0 e to the kt. This should actually look pretty familiar. Doesn't this look like your PERT formula? Pe to the rt. Pe to the rt is a solution to that differential equation dy dt is equal to ky. So that's the solution to our initial value problem. So, exponential change. Y is equal to y sub 0 e to the kt, or PERT as we commonly know it. If your constant k is positive, if your rate up here is positive, then the equation represents growth. If your rate is negative, then your equation represents decay. Remember, if we said that this r was negative, in terms of radioactive decay, it means that the amount of carbon in that object over time was going down. Okay, so let's talk about some different applications of these differential equations. Continuously compounded interest. If the interest is added continually at, and I put this in bold red, a rate proportional to the amount in the account, then you can model the growth of the account with the initial value problem. dA dt is equal to RT. My rate is proportional. I just made my R what was my K to the amount in the account at the very beginning. My initial condition is A of 0 is the amount in the account at the very, very beginning of time. The amount of money in the account after T years of an annual interest rate R is given by A of t is equal to A sub 0 e to the RT, PERT, right? Let's see why. So we're going to go through and separate out these variables and show you why this is the case. So dA dt is equal to Ka, or Ra in the past. So I send my dt to the other side. I divide off my big A, so I have my A and dA together, and my t's and dt's together on the other side. So I have 1 over A dA is equal to K dt, and when I now integrate both sides, my 1 over A is the derivative of the natural log of the absolute value of A, and then the integral of K dt is just Kt plus C. And now I'm just going to solve this for A. So I raise everything to the base of e. So I now have the absolute value of A is equal to e to the Kt plus C. I rewrite this as e to the C, e to the Kt. And so A is equal to plus or minus e to the C, e to the Kt. So when we get to the end, and we've said that the plus or minus e to the C is now A sub 0, we have A is equal to A sub 0 e to the Kt, and that is PERT, the amount that you put in the bank, e to the rate that it was put in there at for however many years that you have it in there. So let's talk about some real life examples. Continuously compounded interest. If money is invested in a fixed interest account where the interest is added to the account k times per year, the amount present after t years is A of t is equal to A sub 0 times 1 plus R over k to the Kt. This is if it's compounded a certain number of times a year. So if it's compounded twice a year, your k is 2. If it's compounded quarterly, your k is 4. And we use that whenever we have bank accounts that have a fixed number of compoundings. If the money is added back more frequently, you end up making more money, obviously, because if it gets compounded more often, then that's good. You get more money. The best you can do is if the interest is added continuously, or every second of every minute of every hour. However, the bank doesn't decide to employ some clerk to just sit there and continuously calculate your interest with an adding machine. So they instead calculate the limit as k goes to infinity. Does that make sense? The limit as k approaches infinity of A sub 0 of 1 plus R over k to the Kt would be if I am compounding that every second of every minute of every hour. But we won't really learn how to find this limit in this course. Since the interest is proportional to the amount present, the equation ends up becoming the solution to that differential equation. A is equal to A sub 0 e to the RT, or PERT as we know it. Radioactive decay is also the same way, except we are decaying over time, so our K value is negative. So the equation for the amount of a radioactive element left after time t is Y is equal to Y sub 0 e to the negative Kt. This allows the decay constant K to be positive then, if we just make our whole equation have that negative symbol in it. The half-life is the amount of time required for half of the material to decay. So how would we find half-life? We have this PERT formula out here. This Y sub 0, remember, is the amount of radioactive decay at time 0. So if I want to find the half-life, I want to figure out the amount of time it will take for half of my original amount to decay. My Y sub 0s will cancel if I divide them off. So I'm left with then, to get rid of my e, the natural log of 1/2 equals the natural log of e to the negative Kt. Laws of logarithms tell me that if these two items are divided, I can expand them with subtraction. So the natural log of 1 minus the natural log of 2 is then equal to just negative kt. Natural log of 1 is 0. So we have negative natural log of 2 is equal to negative kt. If I divide off that negative, I have natural log of 2 is equal to kt. If I divide off my k, my half-life is the natural log of 2 over k. That's the amount of time it would take for half of my item to decay. So our half-life is dependent only on our k value, or our rate of decay. And that is it. We'll do lots of examples. We need to get better at separating our variables out. Continue to pay close attention to detail, and we're going to do everything we can to get you ready for this AP test. So we will talk to you later, everybody, and have a good night. See ya!